Before we begin, I'll quickly go over some of the webinar features. For audio, you have two options. You may either listen through your computer or over your telephone. If you choose to listen through your computer, please select the mic and speakers option in the audio pane. If you choose to dial in by phone, please select the telephone option, and a box on the right side will display the telephone number and audio pin you should use to dial in. If anyone is having technical difficulties with the webinar, you may go to contact GoToWebinars help desk at 1-888-259-3826 for assistance. If you would like to ask a question, we ask that you use the questions pane where you may type in your questions. Also, the recording of today's presentation will be added to YouTube at the link provided on this slide or emailed out to you. So now I'm just going to introduce the agenda for today. Today's webinar is centered around a presentation and panel discussion from our expert speaker, Dr. Kamide from Japan, and it will be around Generation 4 reactor technology and how it can interact with renewable technology. Our speaker today will be introduced by Takehiro Sasagawa, also from Japan, and I'll turn it over to him now. Following the presentation, we will have a question and answer session, and then go from there.
Thank you, Jordan. Today's presenter is Dr. Kamide. This is Takehiro from Japan. Dr. Kamide is a vice chair of Generation 4 International Forum, GIF. His mission as a vice chair in GIF is a market issue for deployments of Generation 4 reactors. His concern is contributing of Generation 4 reactor systems to sustainable energy society. He's working for Japan Atomic Energy Agency as a Deputy Director General for sector of fast reactor and advanced reactor research and development. Please join his talk about harmonization and advanced reactors and renewable energy systems. Thank you. This is the end of the introduction of Dr. Kamide. Thank you.
Yeah. Thank you very much. Thank you to join this webinar for the generation reactor system and renewable energy. Let me talk about how the generation for reactor system can work in the future energy society together with renewable energy. Next slide, please. This view graph shows the content of the presentation. Firstly, I'd like to introduce what is the Generation 4 International Forum, and secondary relation between the nuclear and renewable, and what can be done by Generation 4 reactor system. And lastly, I'd like to talk about the challenges for the industrial deployment for Generation 4 reactors. Next slide, please. Yes, the first item is the Generation 4 International Forum. Next slide, please. Here you can see the generation of the nuclear energy system. Current nuclear plants in operation are mainly Generation 2 and Generation 3 reactor. It's a light water reactor using light water as a coolant. Evolutionary light water reactor and small modular reactor and Generation 4 reactors are expected as the next generation of the nuclear power plants. These Generation 4 reactors are expected to enter commercial phase after 2030. Next slide, please. Here you can see the history of the Generation 4 International Forum, GIF. Firstly, USA proposed a bold initiative in 2000. The vision was to leapfrog light water reactor technology and collaborate with international partners to share R&D on advanced nuclear system. GIF Charter was signed in July 2001 and extended in 2011. Generation 4 concepts defined via technology goals and legal framework, as I talked later, and technology roadmap released in 2002 and updated in 2014. So we have a 2-year study with more than 100 experts worldwide, nearly 100 reactor designs evaluated and down-selected to the 6 most promising concepts: SFR, sodium cooled fast reactor, and VHTR, very high temperature reactor, and LFR, SCWR, GFR, and MSR, like lead cooled reactor, and supercritical water reactor, and gas cooled reactor, and molten salt reactor. These are the 6 ideas for the generation reactor system by GIF. And framework agreement was signed in February 2005 and extended in 2015 for another 10 years. And now France, Japan, Korea, USA are signed in February 2050, and Russia, Switzerland, South Africa signed after February in 2050, respectively. China and the EU 2016, and recently Australia joined in 2017, and also UK signed its instrument of accession in 2018 as new member countries. So the GIF are now also growing at this moment. Yeah, next slide, please. Here is a generation for goals. For these goals, as I said before, the 6 reactor systems are selected to fit these goals. So these goals are very important for the generation 4. First is the sustainability, long-term use of the nuclear reactor system, so we can need a long-term fuel supply. And the other is to minimize waste and the long-term stewardship burden. So this is also very important to become the very waste minimization is an important issue. And safety and reliability is also very important. So very low likelihood and degree of cover damage and eliminate the need for the offsite emergency response. You can imagine the Fukushima Daiichi nuclear power accident. I also touch this matter later. And the third one is economics. Life cycle cost advantage over other energy sources, and financial risk comparable to other energy projects. So economics is very important to employ to build the generation 4 reactors in the current market. And the proliferation resistance and physical protection. So unattractive materials diversion pathway and enhanced physical protection against terrorism is also a very important issue for the nuclear utilization. Next slide, please. Here you can see the 6 generation 4 reactors. Left-hand side, the top is the sodium-cooled fast reactor, SFR. There are 2 types of the design, full-type reactor and the loop-type reactor. And middle top is a very high-temperature reactor. This reactor uses the argon gas or helium gas of the gas coolant, and using carbon matrix for the fuel containment. And the gas-cooled fast reactor, this is a gas-cooled reactor, but a fast neutron reactor. Very high temperature reactor is normally using the carbon, so this is not the first neutron reactor, normal. The supercritical water cooled reactor and the lead-cooled fast reactor. Lead-cooled fast use lead as a coolant, and the molten salt reactor. It is a little bit different idea from other. This reactor using the molten salt fuel as a fission and to convert the energy to the energy conversion system. That this molten salt fuel can be used as a coolant itself. Okay, next slide, please. Here you can see the comparison of the generation 4 reactors. The vertical axis is a 6 reactor system, and the horizontal axis is a neutron spectrum, coolant, what is current at the temperature range, and what is the fuel cycle characteristics. Here you can see the neutron spectrum, fast and thermal. Here is a neutron in case of the fission, we have a neutron, and this neutron make a chain reaction of the fission. But this neutron has the energy at just after the fission, very high energy and fast neutron. The fast spectrum neutron reactor using this kind of the high energy neutron. And the thermal, there is a thermal reactor, VHTR, or some kind of SCWR, also some kind of the MSR. This thermal reactor uses a very low energy, low speed neutron. This is some kind of the change in this generation 4 reactor, and fast neutron has effective to use the uranium and also to combat the plutonium and minor actinide. This is a very important point. And also here you can see the outer temperature range is a very higher temperature, larger than 500 degrees Celsius. In case normally the light water reactor is around 300 or 350 degrees Celsius, so the higher temperature can be achieved in the generation 4 reactor. Okay, please, next slide. Okay, here you can see the 14 current members of the GIF. This is a ABC order: Argentina, Australia, Brazil, Canada, Republic of China, and Euratom, France, Japan, Republic of Korea, Russia Federation, and the Republic of South Africa, Switzerland, UK, and United States. These are the members. Okay, next slide, please. Okay, after the introduction of the Generation 4 forum, and nextly, I want to speak about the relation between the nuclear and renewable. This is also the main issue of this presentation. Okay, next slide, please. As you know, in Japan, we have a Fukushima Daiichi nuclear power plant accident 7 or 8 years ago. And this big graph shows the current status. Left-hand side, we have a mid and long-term roadmap towards the decommissioning of the Fukushima Daiichi nuclear power plant station. On the right-hand side, you can see the conceptual diagram of the area of the under evacuation. So at this moment, so 7 years later, many of the people, over the 40,000 of people, are still evacuated because of the release of the radioactive material. So in this Fukushima Daiichi nuclear power plant accident, no one is died, but directly to the accident. But you can see such over 40,000 of people are evacuated from their home. So the society was a very large influence, or such a accident influence was you can see. So the safety is a very important issue for the nuclear, not only the light water reactor, but also the Generation 4 reactor. Okay, next slide, please. Here you can see the need for the carbon dioxide-free energy. As you know, we have global warming, and the decarbonized society are needed. This big graph shows the carbon dioxide release in every year, and it is increased up to now. But according to the Paris Agreement, COP21, we have to reduce these carbon dioxide emission towards zero in 2100. So it means we need a reduction every year, 0.4 gigatons of the carbon dioxide. And then if we can consider the nuclear, more than 66 gigatons of carbon dioxide emissions have been avoided through the use of nuclear energy since 1971. So the nuclear electricity has a large role for the carbon dioxide reduction. And at this moment, 1.7 gigatons of carbon dioxide every year avoided by using the nuclear. So you can imagine that nuclear energy can contribute to such a reduction of the carbon dioxide. Next slide, please. And here is also some topic in Japan. In this year, summertime, we have a very large earthquake in Hokkaido. The left-hand side map shows the Japan island, and the North Island name is Hokkaido. The area is almost near the island. So such a big island is Hokkaido. As an earthquake in this summer resulted in the blackout of the electricity in the entire area of Hokkaido, in such a very large area, for several days long. So large thermal power reactor, which covered half of Hokkaido, was shut down by the earthquake. And the total of around 3 million households lost the electricity for a long time. Such a large-scale blackout is the first time in Japan. So this event shows us the reliability of the grid is very highlighted. So such a widespread blackout occurred all over the world, and stable and reliable grid is a significant issue of the electricity supply. This is also the relation issue with nuclear and renewable energy. So I speak this event in Hokkaido. Please, next slide, please. Here you can see again goals of the Generation 4 reactor system. As I said before, safety or reliability or long-term use. Here you can see the Generation 4 goals very several years. So many years ago, we have set such goals. This sustainability and safety and reliability, economics and purification, resistance, physical protection are still very important goals you can understand as I might talk. Okay, next slide, please. Here, there is some ways for the Generation 4 reactors to commercialize. We have a 6-reactor system, and here is the common attributes and challenges. Reliable and sustainable power supply in the decarbonized society is very important, and such a nuclear reactor system can provide such a reliable power supply system. And safety enhancement, it depends on the reactor types, but each of the reactor system has a higher possibility to reach such a higher safety enhancement. And the third one is cost competitive with these attributes. So such enhancement of R&D collaboration on these issues are important to realize the Generation 4 reactor. Next slide, please. Here you can see the worldwide energy policy scenario established by IEA. So here you can see the nuclear is almost stable in this scenario, but solar and wind are increased remarkably. So intermittent renewable like solar panel or windmill emerging rapidly in the world. So dispatchable zero carbon dioxide free energies are about 20%, although intermittent are 30% larger. Okay, next slide, please. Here you can see the example of the daily intermittent patterns of Germany. This big graph shows the daily change of the solar panel in the center, and blue color is the grid consumption. So it's a very normal in the daytime. We have a large production by the solar panel, but no production in the night time, of course. Next slide, please. So there is some type of the renewable energy, and carbon dioxide emission was shown in this big graph dependent on the power supply system. Vertical axis is a kind of the energy system. One is a stable. There is a renewable energy of the stable energy like hydro, and the nuclear is also the stable energy without carbon dioxide. And intermittent, it means such intermittent power renewable energy source, solar panel and wind, and the postal is a lower term. And the horizontal axis is carbon dioxide emission unit per kilowatt electricity per hour. And Sweden, France, and Japan are listed here. And central is energy mix of such an energy system. So you can see that in case of the stable energy source have a higher energy mix over the 80%. The emission of the carbon dioxide is very limited, you can see. But in case of the intermittent contents are large, 50% or 80% in California and Germany, the emission of the carbon dioxide is not so reduced because such as I mentioned before, the intermittent renewable energy needs to compensate the such intermittency by a fossil energy source like fire, coal power plant. Here you can see the 60 or 50% of the energy mix was assigned to the fossil energy system. Including Japan, in such a case, we have a very large number of the carbon dioxide emission. Okay, next slide, please. And the third item is what can be done by Generation 4 reactors. Next slide, please. Here are the multiple ways to commercialization again for the 6 reactor system. And the example of the contributions of the such advanced reactor system and the attributes are listed here. For the hybrid system, here is a several items for the contribution to the hybrid system. One is we need a reliable grid, and nuclear energy system can make to fit such a reliable grid by using load pulling, and also the one of the idea is a heat storage, and also the heat usage for hydrogen making and water desalination, and effective use of uranium resources, long-term use for the sustainability, and minimize the radioactive waste and burden is also very important for the long-term use of the nuclear energy. And also very important is the cost competitive for the commercialization, and we need the R&D for the innovative system like energy conversion system, and also we have several feedback from the Generation 3 experience. Such experience also contributes to the cost competitive. And lastly, the safety is a very significant issue, as I said before. And the passive future using reactivity feedback and passive shutdown system is important for the safety. And the passive decay heat removal, like a natural circulation, is also the contribute to the safety. And lastly, the safety design criteria for the international safety standard. It also contributes to the increase of the safety level of the such a generation 4 reactor. I also touch this safety design criteria later. Okay, next slide, please. Here you can see the example of the hybrid system. So it means nuclear integrate or harmonize with the renewable energy system. You can see the top nuclear power output adjustment for the intermittent energy source of the renewable, like a solar panel. And this combination achieves a constant power supply. And the middle, you can see the example of the very high temperature reactor and renewable energy system hybrid energy electricity provided system. And top side, we have a renewable energy system, and the center of the figure have a very high temperature test reactor. And in case of the daily change of the renewable energy system, like a left-hand side figure, green area is a solar or plus windmill, and the yellow area provides a nuclear for the electricity power supply. Such a load following can make a constant or stable power supply for the energy electricity grid. Okay, next slide, please. This view graph shows an example of the hybrid system, again for the very high temperature electricity, very high temperature gas-cooled reactor. And this graph shows not a load following, but also the using heat utilization or of the hydrogen production. So this hydrogen production is not only important for the electricity, but also the such mobile or transportation carbon dioxide emission can be reduced by such a hydrogen technology. And it contributes to the decarbonized society. Here, this graph shows the IS process decompose the water with the heat of about 900 degrees Celsius of the very high temperature reactor using a chemical reaction of iodine and sulfur for the hydrogen production. The chemical process is a little bit complex, but the point is we need only the water for the input, and also we can utilize 900 degrees Celsius of the high temperature by a very high temperature reactor, and we can get the hydrogen by using such a process. And this is not the idea. We have such kind of the kind of the process technology. Thank you. Okay, next slide, please. Okay, this view graph shows the effective use of a uranium resource for sustainability. As for the sustainability, I said before, we need fuel supply. So the effective use of uranium is a resource for the nuclear. So effective use is very important. And effective use of the natural uranium can be provided by closed fuel cycle and fast neutron. As I said before, fast neutron contributes the utilization of the plutonium by using closed fuel cycle. We use nuclear, and spent fuel contains plutonium as a fission fuel material, and the closed fuel cycle means such a plutonium can be produced by the reprocessing, and it was fed to the reactor again. And such a cycle is named by closed fuel cycle, and this cycle achieve long-term use of the natural uranium. The left-hand side figure shows the nuclear capacity, and there is some scenario, but depending such a nuclear utilization scenario, the right-hand side shows the cumulative demand of the natural uranium, and such demand is easily over the total conventional uranium resources amount, like this view graph. But if we use a fast neutron reactor over the world, such a demand of the natural uranium can be reduced, and we can control the uranium resource below the 15 million tons of uranium conventional resource limit. Okay, next slide, please. Here, the next point is the minimum radioactive waste. If we use a nuclear energy system, the waste management is very important. We have to control such a radioactive waste far from the human being in case of the very high radioactivity material. So burning and the transmutation of such a high activity material with the plutonium and the minor actinide is achieved by fast neutron reactor. The top figure shows the final waste of the radiotoxicity included in the spent fuel direct proposal case is the fuel itself, and in case of the reprocessing case, we have a glass fixed material for the disposal. In case of such a glass pattern, glass cases, we can remove the plutonium and the uranium for the next utilization for the reactor, so the radiotoxicity was reduced so much. And again, in case of the minor actinide, it can be reduced, partitioned, and used by fast neutron reactor. In case of the generation 4 reactors, more reduction can be achieved. And the bottom side figure shows the footprint of the such a waste disposal. In case of the generation 4 reactor, we have 1/20th of the very small area of the footprint can be achieved for the final disposal for the very high radioactive waste. So such a generation 4 reactor has a large good point for the minimization of the radioactive waste. Okay, next slide, please. Here we can see what is a long-term radioactive nuclide. As I said before, actinide nuclides created by the neutron absorption into the uranium have a very long-term radiation activity. One is a plutonium-239. It has a long-term half-time of the reduction, 24,000 a year, and the total of plutonium is 10 kilogram per 1 ton of the light water reactor spent fuel. And for the minor actinide, neptunium and americium and curium has also the longer term of the radioactivity, and some amount of the such a high level radioactive waste was produced as the spent fuel, inside the spent fuel. So we need to control such a plutonium and minor actinide, and these plutonium and mine oxide can be burnable and transmutable as a fuel in fuel fast reactors. It is a very big important point of the fast neutron reactor, like a generation 4 reactors. Okay, next slide, please. Here you can see the flexible plutonium management by fast reactor. As I said before, we can use the nuclear fuel, nuclear energy system. Of course, we have a spent fuel. So this big graph shows the bottom side is a spent fuel storage, and the top side is a nuclear capacity of several reactors. Green one is a light water reactor using uranium as a core fuel, and the red or pink colored was the plutonium recycling in white water reactor. Light water reactor also can use plutonium, but the efficiency is not so high, but it can be used in the light water reactor in the pink colored bar chart. This shows the ratio of the light water reactor power output of the total power is around like a 20% in this case. And the blue color means fast neutron reactor utilization, like 6 or 7 gigawatt electricity was produced by fast neutron reactor. And this case study was applied to the Japanese market of the energy system of the nuclear. In such case, we can control the spent fuel storage. You can see the lower side of the figure. So you can see the total storage of the spent fuel is not increased, including the MOX spent fuel provided by the plutonium recycling light water reactor. So we can manage the contents or we can manage the total amount of the plutonium by using a fast neutron reactor. On the right-hand side case, you can see the light green color of the fast reactor is increasing and occupied the total of the nuclear capacity in 2040 or 50 period. In such a case, so you can see the total transition from the light water reactor system to the fast neutron reactor system. In such case, the remarkable reduction of the spent fuel storage can be achieved by using the reprocessing and provided plutonium and uranium-238 was fed to the fast neutron reactor, and reduction of the spent fuel can be achieved. So you can see the fast neutron reactor is very important and contribute to the management of the plutonium and also the spent fuel storage. Okay, next slide, please. So the last item is a challenge for the industrial deployment of generation 4 reactors. Next slide, please. Here you can see the viewpoint towards the commercial deployment of the generation 4 reactor. There's some point of the viewpoint, but here you can, I want to speak about the economics and also the international collaboration for the R&D. Next slide, please. Of course, in case we want to make a generation 4 reactors for the commercialization in the market, economic challenge is very important. This big graph shows the recent light water reactors cost. Big graph shows the cost. Construction cost, including overnight cost, and also the some increase by the delay of the construction or the some measure for the additional safety requirement. Such a additional cost was also required for the light water reactor, even in the light water reactor. And as for the generation 4 reactors, we need such a cost reduction is a very urgent and big important issues we recognize. Okay, next slide, please. Next slide shows the importance of the international collaboration, and one of the effective activity by the our Generation 4 International Forum is a global standard for the safety regulation for the Generation 4 system. Generation 4 in the Generation 4 International Forum, we have activity to make such a safety design criteria and also the safety design guideline for the improvement of the predictability on regulation for the reactor deployment. Such a safety design criteria and guideline is important for the safety and also the important for the deployment, because when the power utility build a reactor, we need a regulation. But such a predictability of the regulation is very important when such a power utility company try to start the commercialization of the Generation 4 reactor. Okay, next slide, please. So what is the safety design criteria in the Generation 4 International Forum? Start the safety design criteria for the sodium-cooled fast reactor. In order to commercialize the sodium fast reactor system by the middle of this century, building of the international common criteria of safety design, and it should be the flexible within the acceptable range, has become more important. So, SFR, safety design criteria, SDC, to achieve safety goal of Generation 4 system, as I said before, have been developed by the SDC task force of the GIF, which was established in May 2011. The SDC Phase 1 report was already approved by GIF in 2013 and revised recently based on the comment by national regulator and also the international organization like IAEA and OECD GSAR. And safety design criteria revision 1 was opened in GIF website. As I said, the GSAR is a joint CNRA, CSNI of the OECD NEA ad hoc group on the safety of the advanced reactor. So we have a communication with the regulatory people of IAEA and also the GSAR. And the safety design guideline is such a design guide to achieve the safety design criteria as has been developed for the application of the sodium-cooled fast reactor. And this safety design guideline was also have a comment from the WGSA of OECD NEA. WGSA is recently the GSA was changed or advanced to the new name, the Working Group on the Safety of the Advanced Reactor. Yes, the next slide, please. Here you can see the hierarchy of the safety standards. The top are safety fundamental, and we have a safety design criteria and the guidelines, and the lower side is a technical code and standard depending on the country. And such a safety design criteria and the guideline can make a standardization of the safety requirement and also the what is the design measure to achieve such a safety design criteria was worldwide standardization can be achieved such a activity. And also, as I said before, this activity can contribute to the deployment of the Generation 4 reactor system. Okay, next slide, please. Okay, such international collaboration, we have several R&D in GIF and also the OECD NER. This is just an example of the activity. We have a new task force on R&D infrastructure in GIF, so it can promote the international utilization of the large infrastructure. And also we have activity of the Nuclear Innovation 2050 in OECD NER, and GIF also contribute to this NI 2050. It is an international collaboration on demonstration of the key technology. And the lower side, you can see some test facility, for example, as a passive decay heat removal system, and also the core thermal hydraulics under the natural circulation to achieve the passive decay heat removal for the highest safety or the simplification of the economic construction of the sodium-cooled fast reactor or such a Generation 4 reactors. Okay, next slide, please. Okay, thank you very much for the joining my talk, but this is the concluding remarks. As I said in this lecture, higher safety, especially on severe accident, is very important, and Generation 4 goals including this very important issue of the safety and the long-term use of the sustainability and the economy and the PRPP for the security, avoid the safe for the utilization of the nuclear, and not only renewable energy, but a combination with the nuclear has a future for the decarbonized society. So for decarbonized system to address the global warming, stable and reliable grid and affordable energy system, this issue can be done by the load following and the heat usage and the storage of the product and hybrid system with combination by the nuclear. And the sustainability with economy by Generation 4 fast reactor is very important for the long-term use of the nuclear and the very stable energy source combination with a renewable energy source, like a higher efficiency of the uranium use and minimize high-level radioactive waste and burden by plutonium minor actionized burning. And the key factors on deployment of Generation 4 is a policy support with the market for sustainability of long-term and clean air, and also the international collaboration of R&D of above issues of the red colors. Thank you very much for the listening my talk. Thank you very much.
Thank you very much, Dr. Kamide. That was an excellent presentation. We are very grateful for it. We had some questions come in as you were talking, so we have about 5 to 10 minutes now that we'll ask you some of those, and we look forward to your answers. We have them in different categories because they kind of came in for different subjects. So first off, there were a couple of questions on Generation 4 reactor technology specifically. And so I want to ask you those first, and then we have a couple questions about how they interact with renewables. So the first question was specifically about fast reactors. The question was, why does a fast neutron reactor of Generation 4 burn plutonium differently or better than a light water reactor? Can you answer that?
Yeah, thank you. The property of the fission reaction depends on the energy of the neutron. Plutonium and also the minor actionized nuclide can make a fission by the neutron, but this possibility depends on the energy of the neutron, and the higher energy of the neutron can have a larger possibility of the fission of the plutonium and minor actinide. And in case of the lower energy of the neutron, the possibility is low. And in case of the light water reactor, the neutron spectrum is very soft. It means the lower energy of the neutron was utilized in the light water reactor system. So the plutonium and the minor actinide is easily can make a fission by using a high energy neutron of the fast neutron reactor.
Thank you for that. And kind of a follow-up with that, I think one of our listeners was a little confused. Do fast neutron reactors just produce less spent fuel, or do they also consume spent fuel?
Could you repeat again what do you mean about the spent fuel?
Absolutely. So one of the questioners asked, does a fast reactor just have less nuclear waste to come out of the reactor, or can it actually consume some of the nuclear waste from other reactors?
Of course, the fast neutron reactor has spent fuel, and it contains uranium and also the plutonium. And light water reactor system has spent fuel. It contains uranium, plutonium, and minor actinide. And in these spent fuel, reprocessing has been done for such a spent fuel, and plutonium and the uranium-238 as the fuel of the fast neutron spectrum reactor was provided by such a reprocessing. And the fast neutron reactor can use such a plutonium and also the uranium-238 as a source of the fuel.
Thank you very much, Dr. Kamide. So the next question coming in had more to do with the interaction of nuclear and renewables. Yeah. So I guess from that, and particularly maybe from a Japanese perspective, how does nuclear enable renewables, or why do renewables take advantage of nuclear?
As I said in the lecture, the renewable system, especially for the solar panel or the windmill, has characteristics of the intermittent. So renewable energy of the intermittent system needs such a compensate or dispatchable energy, and which should be the clean energy and also stable energy. And the nuclear can be the such a energy system. And also the nuclear has several property or good point for such to fit the such an intermittent energy system. One is load following to change its own energy to fit the renewable energy's output, and also the in case of the advanced or generation 4 reactors, it has a higher temperature than the light water reactors. Such a higher temperature contributes to the heat storage and also the heat utilization. This is not already done in the worldwide, but hydrogen protection also the one of the options, such as utilization of the higher temperature.
Thank you very much for that. And so we had actually two questions come in on the next part, kind of building on that renewable and nuclear portion. Renewable energy is often built very quickly and is rapidly expanding, but nuclear energy takes a long time and does a lot to support grid reliability. And these are kind of separate goals. So I guess, in your opinion, who would be the person to kind of research or build out this kind of joint between the two when they kind of have separate goals? One person asked if you feel like nuclear, because it has such long commercialization scales, should be privately funded research, or if that should be something taken on more by the, I guess, the questioner didn't ask, but who should that fall to if you have these kind of rapidly expanding renewables and longer time scales nuclear?
Yeah. Yeah, it's a very good point and important point, I think. Of course, the player is nuclear energy side, but also important is the grid stability and also the renewable energy system. Together with such a system, we have to make such a harmonized energy system or electric system should be achieved. As for the commercialization of the advanced nuclear reactor system of the such a generation 4 reactor, you are true, it takes a time. And in this long, such a several 10 or 20 years of long of the development of the generation 4 reactors, several variations of the reactor system included, we need to the R&D on the how we can fit the such a intermittent source of the renewable energy like heat utilization or easy to load following, and also the constant nuclear power, but to fit the intermittent energy system, heat utilization, heat storage is also the one of the important R&D theme in this area recently. So such a R&D is very important, I understand. Thank you.
Thank you very much for that answer, Dr. Kamide, and you have done so excellent answering all these questions. We have just 1 or 2 minutes left, so I was hoping to ask you one final last question, and that was basically about the NICE Future Initiative and the Generation 4 International Forum. So I guess what is the interest between these two organizations to work together, and why are you interested in working with this organization as well?
Yeah, thank you very much. Recently, Generation 4 GIF proposed to have a collaboration with NICE Future Initiative. One point of us is if Generation 4 reactors can be commercialized in the next generation market, in such a market, the renewable energy has a very large role we expected. So we need some interaction with the renewable energy system and also the grid. It should be very stable, and grid stability is an important issue to harmonize the nuclear and the renewable energy system. So we need such a communication window with such a people of the renewable energy field and also the grid or energy supply system player. The NICE Future should be a very important chance to talk with such people outside from the nuclear. It's our intention.
Thank you very much, Dr. Kamide. That was an excellent presentation, and thank you so much for answering all those questions. I also want to send a thank you out to all of our participants. We are so glad that you came and attended, and we hope that you can take some of these ideas and insights back to your ministries, departments, and organizations. Please enjoy the rest of the day, your day, and that concludes our webinar, and we look forward to seeing you on NICE Future events.